Hey everyone, welcome back to the channel. So far in this course, we've covered distance, displacement, speed, velocity, and acceleration. From those, we derived the four equations of motion, and after that, we went through motion graphs, how to read them, what the gradient and the area actually represent. Today, we're moving into a new topic, motion under gravity. You'll also hear this called free fall. The two names mean exactly the same thing. We're going to split this topic into three stages. Stage 1, motion downwards. Stage 2, motion upwards. And Stage 3, projectiles. Before we start, one thing to keep in mind for this entire topic. Whether a question states it or not, the acceleration due to gravity g is 9.81 meters per second squared. Sometimes, purely for convenience, we round this to 10 meters per second squared to make the arithmetic cleaner. I want to be clear about this. 10 is not the real value. It's a convenience we use when a question allows it. For today's examples, we'll use 10. One more thing about this acceleration. It is always vertically downwards. Always. That direction never changes, no matter which stage of this topic we're working through. Let's start with motion downwards. The first thing to know here, the object is always moving in one direction only, downwards. There's no upward motion involved at all in this stage. Let's take an example. An object is dropped from the top of a building. Let's give the building a height, say 80 meters, from the ground to the top. A question on this scenario might ask, find the time taken for the object to reach the ground, or find the final velocity. Both are asking about the same moment, when the object reaches the ground. Now, to use the Suvat equations, remember what we established earlier in this course. You need at least 3 of the 5 variables before you can solve for anything. So let's see what we actually have. We already have the acceleration. Since this is motion under gravity, that's g. And for now, we'll take it as 10 meters per second squared, purely for convenience. We also have the displacement, because the question gives us the height of the building. So s equals 80 meters. And we also have the initial velocity, indirectly. Think about it. What is u here? U is 0. And we get that from one word in the question, dropped. The word dropped tells you the object started with no velocity at all. It wasn't thrown, it wasn't pushed, it was simply released. And dropped isn't the only word that tells you this. You'll also come across words like fell and released. Any of these, dropped, fell, released, all mean exactly the same thing. U equals 0. So now we have 3 of our 5 variables. U equals 0, A equals 10 downward, and S equals 80 meters. This is exactly the moment to write your 4 equations down on the side of the screen. I always tell my students, you don't need to memorize these. Write them out every single time you attempt a question like this. Do that for 10 or 15 questions, and by the end, they'll already be locked into your memory without you ever sitting down to memorize them on purpose. So here they are, written out on the side. I haven't written them in any particular order. That doesn't matter. What matters is that they're all visible while you work. Now let's go through them one at a time and see which one actually helps us. Look at the first equation. V equals U plus AT. We have U and we have A, but we don't have V and we don't have T. 2 unknowns in the same equation. That's not going to work. Move on. Next equation. S equals U plus V over 2 times T. We have S and we have U, but again we're missing both V and T. Same dead end. Third equation. V squared equals U squared plus 2AS. Let's check. We have U, we have A, and we have S. That's 3 known values and only 1 unknown, V. This is the one that works. All right, so let's use it to find the final velocity. V squared equals U squared plus 2AS. Remember, we're applying this equation vertically downwards because that's the direction our object is moving in. And downward is the direction we've taken as positive for this entire stage. V squared equals 0 squared plus 2 times 10 times 80. V squared equals 1,600. v equals the square root of 1,600. So v equals 40 meters per second, and that's our final velocity. Now, let's find the time taken. Going back to our list, the equation s equals ut plus half at squared has s, u, and a all known, with only t missing. That's our equation. S equals ut plus half at squared. Substituting in, s equals 80, u equals 0, a equals 10. 80 equals 0 times t plus 1/2 times 10 times t squared. The ut term disappears completely since u is 0. That leaves us with 80 equals 5t squared. Now we divide both sides by 5. T squared equals 16. Take the square root and we have t equals 4 seconds. Now let's move on to motion upwards. This one needs a slightly different strategy, so let's understand it through an example. Imagine an object is projected from the ground vertically upwards at 40 meters per second. For a scenario like this, you might be asked several different types of questions, like find the maximum height reached, find the total flight time, find the time taken to reach maximum height, or even find the duration for which the object is above a certain height, say 50 meters above the ground. Now notice how little information we've actually been given directly. Just this one number, 40 meters per second, projected vertically upward. That's it. But we actually have more than that once we think it through. By default, from what we've already covered, the gravitational acceleration is vertically downward at 10 meters per second squared. And there's a third piece of information hiding in the question itself. At maximum height, velocity becomes 0. The object slows down continuously as it rises, and at the very top of its path, it momentarily comes to rest. V equals 0 at that instant. So just like before, let's write out our 4 equations on the side. I keep coming back to this because it genuinely works. The more consistently you write these out while solving, the faster they lock into memory, without you ever having to sit down and memorize them directly. Now, counting what we actually know, we have u, we have v, and we have a. That's 3 out of 5, enough to get started. To find the maximum height, we need an equation containing u, v, and a, and v squared equals u squared plus 2as fits perfectly. Since the object is moving upwards, we apply this equation vertically upwards, which means we're taking upward as our positive direction for this entire stage. Anything moving downward is negative. So, u is positive since the object moves upward. V is 0, and 0 has no sign to worry about. And a is negative since gravity acts downward while we've chosen upward as positive. Substituting in, 0 squared equals 40 squared plus 2 times minus 10 times h. 0 equals 1,600 minus 20h. Rearranging for h, we get h equals 1,600 over 20, which is 80 meters. And notice, this comes out positive, which makes sense, since the object ends up somewhere above its starting point, in the direction we defined as positive. Now let's find the time to reach that maximum height. We have v, u, and a, so v equals u plus at is exactly the equation we need. Again, applying this vertically upward, v equals u plus at. 0 equals 40 plus minus 10t. So t equals 4 seconds. Time is a scalar, so your answer here should simply come out positive. That's not making a statement about direction, it's just how time works as a quantity. It doesn't carry a sign the way velocity or displacement does. Now let's find the total flight time, the time taken for the object to travel from the ground up to maximum height and all the way back down to the ground again. There are 2 methods for this. Let's look at both. This is the faster method, though not necessarily the one I'd recommend relying on. It gives a correct answer, but it comes with a limitation you need to understand clearly. We already found that the time to reach maximum height is 4 seconds. If the motion is symmetric, the time to fall back down is exactly the same, another 4 seconds. So the total flight time is simply double, 8 seconds. The reasoning behind this, as the object rises, its speed decreases steadily, say from 40 to 30 to 10, down to 0 at the top. On the way back down, at those exact same heights, the speed matches, 10, then 30, then 40 again just before landing. The motion mirrors itself perfectly. But here's the catch. This only works when the object lands back at the exact same height it was launched from. If it lands somewhere higher or lower than its starting point, this shortcut breaks down completely, and you cannot simply double your time to maximum height. Method 2 is the one I'd actually recommend using, even though it takes a bit more work. It doesn't rely on any assumption about symmetry, so it holds up in every situation. For this, we use s equals ut plus half at squared, again applied vertically upward. Think about the displacement here. The object starts on the ground and, after its full journey up and back down, ends on the ground again. Since displacement is the straight line distance between the starting point and the finishing point, and both of those points are the same, the total displacement is 0. So, s equals 0, u equals plus 40, positive since it's launched upward, and a equals minus 10. 0 equals 40t plus 1/2 minus 10t squared, which is 0 equals 40t minus 5t squared. This gives us a quadratic equation. Rearranging this gives us 5t squared minus 40t equals 0. Factorizing the equation, 5t times t minus 8 equals 0, which gives us two solutions. 5t equals 0, so t equals 0 seconds. Or t minus 8 equals 0, so t equals 8 seconds. So why do we get two answers? Because s equals 0 actually happens at two separate moments in this motion. Right at the very beginning, when the object hasn't moved yet, and again at t equals 8 seconds, when it has completed its full journey and returned to the ground. Since the question is asking for the total flight time, we take the answer that makes sense in that context. T equals 8 seconds. Now this method takes a little longer than simply doubling your earlier answer, but it holds up in every scenario, which is exactly why I'd recommend using it as your default approach. Now for the final question in this set, and this one's a genuinely good one to understand properly, because the same method will come up again and again. We're asked, for how long is the object above 50 meters? Once again, we use s equals ut plus 1/2 at squared, applied vertically upward. This time, the question specifically tells us the height, 50 meters above the ground. Since above the ground is our positive direction, we substitute s equals plus 50. 50 equals 40t plus 1/2 minus 10t squared. If we simplify, we get 50 equals 40t minus 5t squared. Dividing everything by 5, 10 equals 8t minus t squared. Then rearranging into standard quadratic form. T squared minus 8t plus 10 equals 0. Solving with the quadratic formula gives two values. T equals 4 plus the square root of 6, or t equals 4 minus the square root of 6. These two times correspond to two separate moments. The object is at exactly 50 meters above the ground, once on the way up and once again on the way down. So the total duration the object spends above 50 meters is the difference between these two times. Delta t equals 4 plus the square root of 6 minus 4 minus the square root of 6, which is equals to 2 square root of 6, which works out to approximately 4.90 seconds. In a physics exam, never leave your final answer as a surd or a fraction. Always convert to a decimal, and this one comes out to 4.90 seconds. So that's motion upwards.